Hello students, about circle already we discussed many things: radius, diameter, tangent, secant, etc. Now we can start theorem 10.1. Before starting this theorem, one basic idea we should know. Suppose this is a point P and this is a line AB. If we join the point P with the point A, then PA will be the distance between the point P and the line AB. Like this way, we can get many distances. Suppose C, D, E, F, G, etc. So out of these distances, all the distances are not obviously equal. So out of these distances, which is the minimum distance? When PE is perpendicular to the line AB, then this distance will be the minimum distances. So PA, PC, PD, PE, PF, PG, PB, etc. all are the distances between the point P and the line AB. But PE is the minimum distance. So when it is possible? When PE is perpendicular to, symbolically I have written perpendicular. When PE is perpendicular to the line AB, then PE is the minimum distance between the point P and line AB. After getting this idea, already studied this before, we are going to start theorem 10.1. The tangent at any point of a circle is perpendicular to the radius through the point of contact. It is a circle. Suppose this is the center of the circle. Suppose the point O is the center of the circle. A tangent is drawn. Suppose AB is the tangent to this circle and P is the point of contact. This is P, it is the point of contact. We have to prove that this OP is perpendicular to AB. So given circle is given whose center is O, suppose radius is R, we can write O R. One more thing is given, AB is the tangent to the circle C. We have to prove OP is the radius of the circle C. Now, to prove we have to prove OP is perpendicular to AB. Let us take a point C other than P. We are not taking point P, we are taking any other point except P, any other point on AB. We have taken a point C on AB. Then we are joining the center of the circle O with this point C. Construction. Taking a point or any point C on the tangent AB, which is other than P. P is the point of contact. We are not taking this point, we are taking any other point. After that, points O and C are joined. To get OC, let OC intersects the circle at the point D. Let OC intersects the circle at the point D. Now proof. This is the part of the construction. Taking any point C on AB, which is other than P. We are not taking P point. Any other point we have taken, that is point C. After that, we have joined the center of the circle and point C. And this OC is intersecting the circle at point D. That is written here. Say OC means OD plus CD. We can write that. OC is equal to OD plus CD. Now OP is the radius of the circle, OD is also the radius of the circle. So OP equals to OD equals to R. Here obviously OC is greater than OD also and OC is greater than CD, because OD plus CD together, if we join, then we get OC. Obviously OC is greater than OD or OC is greater than CD. Okay? We are taking this part. Now, OC greater than OD. In place of OD, we can write OP. Therefore, OC is greater than OP. Or we can write OP is less than OC. Or OP is smaller than OC. So what we got? OP is the radius and one distance OP is less than the distance OC. This will happen, this occurs for any point on AB other than this occurs means OP is less than OC. This occurs for any point on AB. If we take any point on AB, always we will get OP is less than OC. Or if we take another point, suppose D, then OP will be less than OD. If we take any point X here, then OP will be less than OX. So this occurs for any point on AB other than P. That is, OP is the shortest distance, because always OP is less than the distance between center and the point which is located on AB but other than P. Now, OP is the shortest distance. This is the OP, distance OP. This is shortest, means it will be perpendicular to AB. It means OP is the shortest distance. It means OP is perpendicular to, or symbolically directly you can write OP is perpendicular to AB. That is, OP is perpendicular to AB. Here you can write language. Hence proved. Let us discuss this once again. A circle is given with center O and radius OP or radius R. AB is the tangent to this circle at point P. That means P is the point of contact. We have to prove OP is perpendicular to AB. We have taken any point other than P. We have not taken point P. We have taken any other point, that is point C, and we have joined this point C with the center of the circle. So we have got a line segment OC, which is the combination of two line segments OD plus CD. Obviously OC will be greater than OD, means OC will be greater than OP. That means OP is smaller than OC. If we take any other point except P, always we will get OP is less than that distance. So OP is the minimum distance Now minimum distance means it is perpendicular to AB. That means OP is perpendicular to AB. Exercise 10.1. What are the objective questions? How many tangents? Question number 1. It is given, how many tangents can a circle have? Only one tangent. One and only one tangent. Because suppose this is a circle, this is a point, only one tangent we can draw for a circle. Suppose this is radius, this is point of contact P, this is tangent AB. Only one and only one tangent can be drawn through this point of contact P. Question was, how many tangents can a circle have? For one point, one tangent a circle can have. Suppose this is another point, one more tangent we can get. This is another point, suppose Q. This is another point. Suppose this is R. One more tangent we got. Suppose this is tangent T1, tangent T2, tangent T3, etc. Now, how many points are located on this circle? Infinitely many. So, for infinitely many points, we can get infinitely many tangents for this circle. So, here answer will be, question was, how many tangents can a circle have? It will be infinitely many. If the question was given like that, how many tangents can a circle have for one point on the circle? Then answer will be one and only one, because for one point we can get one and only one tangent. But here question was given, how many tangents can a circle have? A circle can have infinitely many tangents, because on a circle infinitely many points are located. For each point we can get one tangent. For infinitely many points we can get infinitely many tangents. Question number 2. Fill in the blanks given. Question number 1. A tangent to a circle intersects it in dash points. Means how many points? A tangent to a circle. Any one tangent, suppose T1, T2, T3, etc. Each triangle is intersecting the circle at one point only, one and only one point. Intersects in one and only one point. Here in the blank portion we can write one and only one, or simply we can write one also. Second, a line intersecting a circle in 2 points is called a, suppose it is a circle, center O, this is a line, intersecting the circle in 2 points. So this is called as secant. We can write the answer secant. Third part. A circle can have dash parallel tangents at the most. Suppose this is a circle. One tangent. It is tangent, suppose T1. Suppose point P is the point of contact, Q is the point of contact. Only two parallel tangents we can get, not more than two. So answer will be 2. A circle can have two parallel tangents at the most. Maximum 2 we can get. Now, fourth question. The common point of a tangent to a circle and the circle is called the point of contact. This is the common point. This point is located on the circle also and on the tangent also. This point is called as the point of contact. The common point, this is the common point, common to the circle also and common to the tangent also. So point of contact. Answer will be point of contact. Third sum we have to calculate. A tangent PQ at a point P of a circle of radius R of radius 5 cm meets a line through the center O at a point Q, so that OQ is equal to 12 cm. Length PQ we have to calculate. This is a circle. Tangent is PQ. A tangent PQ at a point P of a circle. So P point will be here. P is the point of contact. O is the center of the circle. Already we proved that OP is perpendicular to the tangent PQ. OQ, we can join it. OQ is given 12 cm. It is 12 cm. It is perpendicular. Radius is given 5 cm. This is 5 cm. We have to find the length PQ. That means PQ equals to how much? We have to find that. It is question number 3. Length PQ we have to find. Pythagoras theorem. OP square plus PQ square equals to this is right angle, this is perpendicular, this is base, and OQ is the hypotenuse. So OP square plus PQ square equals to OQ square. OP is 5, PQ it is unknown, OQ is 12, here OP equals to 5 centimeter, OQ equals to 12 centimeter, 12 square. PQ square will be 12 square means 144. 5 square is coming this side, it will be minus 25. (144) minus 25. It is 14. 14 minus 5, 9. 4 will become 3. 3 minus 2, 1. And this one will come here. 190. Therefore, PQ will be 119, square root 119 centimeter. Option D is correct. Therefore, option D is correct. Question number 4. Draw a circle and two lines parallel to a given line such that one is a tangent and the other a secant to the circle. It is a circle with center O. Draw a circle and two lines parallel to a given line such that one is a tangent and another is a secant. Suppose this is a horizontal line. And this is the given line. This circle is given, this line is given. One parallel line parallel to this means if it is 90 degree, we have to draw a line which is perpendicular to this horizontal line, and it also should be 90 degree. Then sum of co-interior angles 90 plus 90 means 180. That means this line and this line will be parallel. Suppose this is line L1 and this is line L2. Line L1 and L2 parallel. Now what instruction is given here? We have to draw one tangent and another is secant. This is a tangent. Suppose T1, we have to draw here 90 degree. Then 90 plus 90, 180 degree. It is a tangent and it is parallel to the given line. That means T1 is parallel to, symbolically I have written parallel to. T1 is the tangent parallel to the given line L1. Another it is secant, suppose S1. Secant means it will intersect the circle at 2 points. Suppose it is intersecting the circle at point A and point B, then it is a secant. And if we draw 90 degree, then this 90 and this 90, total is 180 degree. So S1 will be parallel to L1. S1 is parallel to L1. If you think, you don't have to draw this line and this line also, but to show they are parallel, this sum of co-interior angles of the same side of the transversal, that is 180 degree, then the lines are parallel. This is the transversal, this is a given line, this is the tangent drawn. Then this angle and this angle, they are the co-interior angles, both are 90 degree, 90 plus 90, 180, that's why these lines are parallel. That means tangent and the given line, they are parallel. It is a secant, it is intersecting the circle at 2 points, that's why it is a secant. It is a tangent because it is intersecting the circle at 1 point, suppose point P. Now, this secant, if you draw 90 degree here, then this is the suppose transversal, 90 plus 90, 180 means sum of co-interior angles is 180 degree. That means secant S1 and the given line L1, they are parallel to each other. Next topic. This was question number 4 it was. Number of tangents from a point on a circle, the topic. Number of tangents from a point on a circle. Any point, suppose it is a circle, any point may lie, suppose point P, it is lying inside the circle. Then a line passing through this point, suppose this is line L1, it is passing through this point. Which point? That point is located inside the circle. We cannot get any tangent because this is a secant. Now, two more cases are there. Suppose the point is located on the circle, then we can get a tangent. Suppose T1 is a tangent, and we will get one and only one tangent for a point located on a circle. We can get one and only one tangent. Next, so what was the first case? Point P was located inside the circle. There no tangent. We cannot get any tangent. Now second case, the point P is located on the circle. There we can get one and only one tangent. Now one more situation. Suppose the point P is located outside the circle. Then suppose this is the point of contact A, this is the point of contact B, center of the circle. We can get two and only two tangents for a point located outside the circle. This point P is located outside the circle. We can get two and only two tangents. Now PA is the distance, PB is also some distance, means length. PA is a length, PB is also a length. PA and PB are called as the lengths of the tangents. PA and PB are called as the lengths of the tangents. Now one more theorem is coming, that is 10.2. Theorem 10.2. The lengths of tangents drawn from an external point to a circle are equal. Suppose this is an external point P, PA and PB are the tangents. Length of tangent PA is PA only and PB is PB only. This is the center of the circle O. What are the given points? A circle with center O, a circle with the center O, PA and PB are the tangents to the circle PA and PB are the tangents to the circle. We have to prove PA equals to PB. That means the lengths of these tangents are equal. That we have to prove. Construction. OA, OB and OP are drawn. That means we are joining the points A and O to get OA. We are joining the points B and O to get the line segment OB. We are joining the external point P with the center O to get OP. Now proof. OA is the radius, AP is the tangent. OA is the radius and AP is the tangent. In theorem 10.1 we proved that radius is perpendicular to the tangent. So OA is perpendicular to AP. OA is perpendicular to AP means OAP, angle OAP is 90 degrees. Similar reason we can give for PB. Similarly, OB is perpendicular to BP and OBP is 90 degree. Next point. Take these two triangles. This is one triangle. It is right triangle. This is also another triangle. It is also a right triangle. In triangles OAP and OBP, we are taking two triangles OAP and OBP. Both are the right triangles. First point. This angle and this angle, both are right angles. We can write this angle equals to this angle. OAP. This angle will be OAP. OAP. This is 90 degree, right angle. Then OBP means OBP. This is right angle, 90 degree. So we can take this one, OAP, and this one, OAP equals to OBP equals to 90 degree, right angles. Now, opposite to right angle, opposite to angle A, side is OP, that is hypotenuse, and opposite to angle B, it is also side OP, it is also hypotenuse. Second point, OP equals to OP. This is the common side of both the triangles, so must be equal. It is hypotenuse. OA is the radius of the circle. OB is also the radius of the circle. Both are equal. Third point, OA equals to OB. We can write radii of same circle. So right angle, hypotenuse, side. We can write the next point. Therefore, this triangle OAP is congruent to the triangle OBP. RHS rule or RHS congruency. Since these two triangles are congruent, we can write AP and BP, they are equal. Therefore, AP equals to BP. Congruent parts of congruent triangles are also equal. Hence, proved. So next day we can start exercise 10.2. 2 days over.